brief introductions. I'll introduce Dave here in just a sec, but for those folks, there are a couple new people calling in, I think this month. So a little background on our Permafrost Collaboration Team within IARPC. So our mission statement is advancing understanding of processes, controlling permafrost dynamics, and the impacts on ecosystems, infrastructure, and climate feedbacks. So we try to have one of these calls every month, but we do miss a month here and there. When was the last call, Meredith? I think it was back in a joint call with the terrestrial team back in October, November, sometime back then. Like what we try to focus on during these calls is bringing people together, discussing some current issues and studies going on in permafrost terrains in Alaska and across the circumpolar north. We like to try to bring together presentations or presenters that can focus on like the linkages in the natural system with some of the social systems and some of the feedbacks in the climate system. And there's basically four key issues that we try to address typically. The foundation is Arctic system sciences. A secondary factor is effective Arctic stewardship. A third one is national defense and homeland security. And fourth and foremost is health and well-being of Arctic residents. So I'm happy to introduce Dave today. He'll be touching on permafrost and ecosystem interactions. Dave is I would call him a highly interdisciplinary scientist. He works for the National Park Service office here in Fairbanks, Alaska. He has a long career, I'd say, centered on the intersection of soil sciences, botany and ecology, as well as permafrost and periglacial processes. As Dave mentioned in his intro, he leads the Arctic Inventory and Monitoring Network in Alaska. And through that Arctic Inventory and Monitoring Network, he and his team have been monitoring trends in near surface ground temperatures over time in the Northwest Arctic parks of Alaska, documenting the initiation of thermokarst and thermal erosional landforms and features across that Arctic network, and then also studying their dynamics as they kind of grow, evolve, and interact with climate change in the landscape and potentially stabilize over time. So with that, I'll kick it off to Dave. He's going to give a presentation on permafrost monitoring results from Alaska's national parks, and then I'll also in the chat I'll paste a webpage link to their the NPS Arkin resource webpage on permafrost. So go ahead, Dave.
Okay, I'm going to share my screen here. Okay, you should. I hope I'll see my PowerPoint now. Is that correct?
Yep, looks good.
Okay.
Yep, looks good.
All right. Thanks everybody for tuning in this morning. And I'd like to just share with you some of our recent kind of more interesting findings from our permafrost monitoring program that we have going on at the National Park Service. We monitor a lot of things as part of the Inventory and Monitoring Network, and permafrost is, of course, one of the most important things. So we have that included as a part of one of our vital signs, as we call them. And the way we go about monitoring permafrost in the Arctic network is we have a network of weather stations or climate monitoring stations. It's scattered around all of these national parks. And we monitor, in addition to the usual meteorological variables, we monitor ground temperatures. And these are shallow ground temperatures, a meter or less depth. But as most of you are familiar with these, if you can compute mean annual temperatures in the ground like this, it's very useful for understanding the stability of the permafrost that may be another half meter or more down. And then we also monitor permafrost-related landforms by remote sensing, and I'm going to talk a little bit about some of our most recent findings there too. And specifically then we have a post-2013 temperature shift, and we've also been monitoring slope failures. And so I'm going to look at the kind of the relationship between those two things. So just to give you a some background about the study area. This is the Arctic Inventory and Monitoring Network location, and you can see in the inset map down on the right there is where we are in Alaska. These are 5 national park units. Most of them are in the Brooks Range, and we're also on the northwest coast of Alaska and the Seward Peninsula. And you can see there's this network of these climate monitoring stations scattered across the network there. And these are maintained, they and the data are maintained by Pam Suzanis and Ken Hill of the National Park Service, and they're co-authors on the temperature study here that I'll be talking about. And so besides the Arctic, what we call the Arctic Network of National Parks, we also have the Central Alaska Network of National Parks, which I don't normally work for, except we included that data in this study of the temperatures. And you can see we have these climate monitoring stations scattered also across the parks of the Central Alaska Network, which you can see the inset down here in the lower left. These are parks that are located in mostly in southern and eastern interior Alaska, Denali National Park, Yukon-Charlie Rivers National Park and Preserve, and Wrangell St. Elias National Park. So the temperature data that I'm going to be presenting to you is from these stations, most of which were installed between about 2005 and about 2011. But I also am going to show you, we also of course look at the data from the National Weather Service stations in the vicinity, because those have longer records and are really helpful for understanding what's going on. And so I'm going to show you one of those longer term records at Bettles as an example of this 2013 temperature shift that is the big event that we've noticed in recent years at all of our stations too. So anywhere where you have a record spanning 2013, there's in this, in interior Alaska at all of our stations anyway, and Northwest Alaska where some of our parks are, you see this abrupt shift to higher mean annual temperatures that seem to have begun about somewhere in the fall of 2013. And I'm showing you Bettles here because that's a good example. They basically all show the same thing. This one is just a nice example with a good long record going back to 1950. And as you can see, there was a shift to warmer temperatures that occurred abruptly in 1976 and was first described by Hartman and Wendler. And then for several decades after that, in many places over most of interior Alaska and northwestern where we work, the temperature was obviously variable, but this is mean annual temperature now. We're talking about mean annual air temperature. The mean annual air temperature was pretty flat, highly variable, but no real trend. And that changed suddenly at the end of 2013 when the temperatures went up. In this case, the mean went up to about 1.7 degrees at Bettles. And you can see the means here that I've plotted with horizontal lines. And I've also plotted a shorter term mean here, the 2006 to 2013 mean, because that's actually the time span where all of our weather stations in the national parks actually were installed. So we are sampling this period that's really towards the end of this long flat spell, and that it was actually a little colder. The mean annual temperatures were actually a little bit colder during that period than through the 30 years. So our results may exaggerate the amount of change a little bit, although it's definitely real. And so, of course, the question for those of us interested in permafrost is, what did this do in terms of permafrost stability? And before I leave this slide, I should mention that the amount of change in air temperature ranged across our study area from 1.1 degree Celsius at Gulkana to 3.4 degrees Celsius in Kotzebue. So this temperature shift that occurred was generally the smallest in southeastern interior Alaska, and it increased as you moved to the northwest. So it was more in Denali Park, and it was more, and then the highest one we got was out in Kotzebue, 3.4 degrees, and Nome was pretty high too. So the increase as you got towards the coast was more. So what effect did this have on permafrost, which is what we're curious about. And so what you see here, this graph, which I'll spend a little bit of time on, is we've plotted along the x-axis the change in mean annual air temperature from 2006 to 2013, in other words, pre-warming, to 2014 to 19 post-warming, which is, I showed you was, between 1 and 3 degrees. And we've plotted that versus the observed change in mean ground temperature, which is on the y-axis, at all of our climate stations around the parks that I just showed you that had, we felt, a decent record prior to 2013, although not necessarily all the way back to 2006, but far enough that we felt we had a handle on what it was prior to the 2013 shift. And so what we can see then is, what did the ground temperatures do? Did they also change by 3 degrees, the mean annual temperatures? And would that imply then that the temperature at the top of the permafrost went up by 3 degrees or not? And I've plotted these y equals x and y equals 0.5x lines to show you, to illustrate where the temperatures, where y equals x, the mean annual ground temperature change, then went up as much as the air, while the points along y equals 0.5x, they went up only half as much as the air. As you can see that out in the Arctic network, this circle here up in the upper right, the mean air temperature change was greater, which is, what I just showed you, is out in Northwest Alaska, we had more change. And particularly at these points that are brown colored, it was nearly a 1-to-1 change in ground temperature compared to air temperature. And the brown is what we've labeled as scoured snowpack situations. So we had quite a few sites that were up on these kind of rocky ridge tops where we could get a good view of our satellites that we used to telemeter the data back. And so those were kind of windblown and had thin snowpacks, less than 20 centimeters at their maximum on the average. And the other snowpack terms here come from the Matthew Sturm et al.'s classification of snowpack types. Tundra snowpacks are the thin, cold and wind-packed ones, and scoureds are actually just a kind of a subset of the tundra ones. And as you can see, at these scoured sites, there was pretty much a 1-to-1 change in ground temperature compared to air temperature. In the Central Alaska Network parks, the amount of change in air was, in the mean annual air temperatures, was closer to 2 degrees or less, and you can see that the ground temperature change was not quite up to the same magnitude as the air temperature change. So we were more hanging around a 1 degree change in air temperature, or excuse me, in ground, corresponding with the 2 degree change in air temperature. And we think that was due to the different, mainly to the different type of snowpack that we had at those sample sites. We had many more stations that were of these taiga and alpine snowpack types, which are deeper and better insulators. And so it turns out that the response to air temperature change seems to be muted by essentially a more insulative snowpack. And that, for those of you who are interested in the details of modeling that, we can demonstrate that by looking at N factors and that sort of thing. So anyway, just to summarize then, in the Arctic parks, the mean annual air temperature change was near 3 degrees, and the ground temperature change seemed to be close to that also. Although at places where there were deeper snowpacks, which we didn't have much in our sample here, there probably were lesser changes of more like 2 degrees. In the Central Alaskan parks, the mean annual air temperature change was near +2, and the mean annual ground temperature change were probably about +1. So of course, the implication there is warm permafrost then is going to potentially become destabilized by these temperature shifts in the ground. Well, those of you who might be thinking, oh, what about thermal offset? That's something that falls out of the equation as long as it doesn't change pre and post warming. So so that shouldn't matter a whole lot. That's one nice thing about being able to monitor just shallow ground temperatures. So anyway, what I'd like to show you next is we have some maps here of mean annual temperatures at the top of the permafrost that were done by modeling using the Physical Institute Permafrost Laboratories model that Santosh Panda ran for us a few years back. And here you can see now what I've highlighted in yellow and red are the areas that are that in the 2000 decade had permafrost temperatures that were above -2 Celsius. And you can recall then that we thought that there was, probably at least 2 degrees of ground warming during that recent 6-year period. Of course, whether or not that will stick is another question. It seems to be continuing to be quite warm this year too. But in our analysis period, based on our analysis period of the last 6 years, these areas that are red and yellow should be starting to undergo some permafrost degradation as a result of simply bringing the temperature at the top of the permafrost above freezing. And this, of course, is not talking about active layer increases, which could occur anywhere, right? That isn't. We're talking about mean annual temperature. As you can see, that those areas that are red and yellow are kind of concentrated in the valleys, lower elevations on the south side of the Brooks Range, and the bulk of these parks in blue here had ground temperatures that were colder than -3 to start with, and so they should still be. They may be experiencing some active layer increases, but they should still be okay in terms of the bulk of the permafrost. And now I'm going to move down to the parks in central Alaska. Here on the left, we have Denali National Park, which is B on the inset map here, and Wrangell St. Elias National Park, which is C on the inset map. And these are in interior Alaska is where that permafrost is. And here I've changed the scale to reflect the fact that the warming was less pronounced in this part of the country. And so in yellow, I have areas that were modeled as being above -1 Celsius, and red as being above -0.5 Celsius. And you can see then that there are substantial areas that were within a degree of freezing prior to this temperature shift that occurred in 2013, and we're probably looking at some permafrost degradation starting to occur in these locations that are labeled yellow and red. So now the next question that comes up is we're also monitoring landforms, right? And one of those projects that we have got several things we're doing with our landform monitoring, but one of them is to monitor these slope failure landforms that are pretty common around the Arctic network. And this bit of work here that I'm going to report now is restricted to the Arctic network, where I do most of my work. And of course, there have been some high-profile slope failures in Denali National Park, and I'm not going to talk about those today. I'm going to talk about our work in the Arctic network. And what I've been doing is monitoring active layer detachments and retrogressive thaw slumps in the Arctic network. And these are relatively easy to map because you've got bare ground contrasting sharply with green vegetation. Active layer detachments are thin landslides that move basically all in one thaw season, triggered probably by extra deep thaw. Sometimes rainfall probably is involved, and certainly warm weather is involved. Retrogressive thaw slumps grow for multiple years along an escarpment. Both of these, of course, can expose bare soil to erosion and affect lakes and streams, etc. And so what I did was back in a few years back when we first got wall-to-wall coverage of the Arctic network in high-resolution satellite images, which at the time were Iconos satellite images, I did a wall-to-wall Arctic network-wide map of these features. And I'm not going to go into the methods here today, but I'll just say that it was semi-automated, so that made it possible, but fairly painstaking. And anyway, what I did was I managed to locate hundreds of both retrogressive thaw slumps and active layer attachments. And our feeling at the time was that, from people that were flying around the country there said there's a lot of these right now. This is on these images from 2006 to 2009, and people who were flying around the country at that time said, boy, there are a lot of these. This is something we're not used to. And Andrew Balser did a PhD thesis on this also, where he studied using radar imagery, the inception of retrogressive thaw slumps, and found that they indeed did really pick up in this time period, probably due to unusual weather in 2004. And there was also some other warm summers, 2007 in particular, that probably are responsible for bringing the number of these things up for this sample that we made from 2006 to 2009 imagery. So then the question is, okay, what's happened since, and was that how did that compare to historical levels of these features? And so what I did was I chose 4 study areas that I could get imagery from an earlier time and a later time, and basically remapped them. And so you can see these four study areas, and they were also areas areas where I could get imagery, and areas that what I knew to be susceptible to these features from previous from this wall-to-wall map. And so here's the imagery I used to try to make this comparison. Episode 2 in the middle here is the one I've been talking about, Iconos Color IR satellite images from 2006 to 2009. I also mapped these study areas on Color IR aerial photographs that were digitized and orthorectified from around 1980, the so-called AHAP aerial photos, similar in resolution and also color infrared. And so I was able to apply the same methods. And then episode 3, I bought some WorldView 2 and spot satellite images, also in the 1 to 2 meter resolution range, color infrared. So that gave me 3 time slices to try to compare to this episode 2 and see how it was similar or different. And here's an example of active layer detachment history in one example location. On the left, you can see a 1977 AHAP aerial photo, and they're labeled with the 1 as 1 active layer detachment. This is a sloping down to a stream that you can see at the bottom of the scene. And in 2006, that active layer detachment had revegetated, but we had several new ones here that were labeled 2. And then on the 2019 image, they had all grown over. And this was kind of the impression that we had from flying around the country, was that there really hadn't been anything like 2006 since, in spite of the warming. And that was kind of interesting. And one of the reasons I did this quantification here was because I wanted to verify that, is this right, that even though the temperature's been coming up, that we still haven't had a response in terms of slope failures. And so here's these bar plots are, show quantitatively what was going on. And what I have here is the top 2 are study area 1, the first box way over on the left, where we studied this during the 3 episodes. And you can see the 3 bars represent the 3 episodes. I tabulated both the count of these features and the area of the features. And as you can see in study area 1, indeed the middle bar, which corresponds to the Iconos images in this study area, 2007 to 2009, was distinctly more than on the AHAP images or the more recent images. So in 1979, there was fewer, and in 2018, there was definitely fewer of these slope failures. This is area of bare ground exposed on the right, and number than there was in the early and late episodes 1 and 3, there was definitely less, and it shows that this 2007 to 9 event was certainly exceptional. And that was study area 1, which had mainly active layer attachments. Study area 2 was an area that was dominated by retrogressive thaw slumps. Same general trend was that this episode 2, the 2000 decade, definitely there were more area of these things, and they have revegetated since. And this is something that other work that we've done seems to have implied, is that we just haven't had an initiation event like that 2000 decade 1, and we've been mostly revegetating these things since then. Study areas 3 and 4, yeah, maybe a little more interesting here. In study area 3, we actually had similar levels of these features on the AHAP images in the late 70s to what we saw in the mid 2000s. And again, right now we've got, or at least as of 2019, we had distinctly fewer, in this case, active layer attachments in study area 3. And then study area 4, surprisingly enough, there was actually more of these slope failures in in the early times and back there around 1980 than there was at either time since. So indeed, our subjective impression from the time we spent out in these parks was that there really hadn't been um, a new slope failure event that compared to the one that occurred before, in spite of the warming temperatures. Um, uh, the exception here, which I'll talk about in a sec, is these here in the lower right bar plot. You see this thing called DFDL. That's destabilized frozen debris lobes, and that is something that did increase, and that's something else, and I'll talk about that in a second. But just to summarize the active layer detachments and retrogressive thaw slumps, then, why were there so many in episode 2 and not episode 3 in spite of the warming? And the best explanation that we've got at the moment is that these slope failures are triggered by deep summer thaw events, such as the one that occurred in 2004. They can also be triggered by fires and extreme rainfall. Fires were not a big factor in this study area. Rainfall might have been. We really, we don't have a lot of good idea of if there might have been local rain events too. So that may have been a factor in the mid 2001s also. And then, so what's been going on more recently? Well, the post 2014 warming has been concentrated in the winter, and apparently no big new summer thaw events to set off more of these little landslides. And apparently the most susceptible places slid in the 2000 decade, and we just haven't had any extremely deep active layer thaw events since then to set off anymore. And it's also still cold enough in most of the Arctic network, that's being the Brooks Range there, except on those southern valleys probably, that the main mass of the permafrost has remained stable, and there isn't any progressive talic development happening up there because we started off colder than -3. Remember that graph or that map I showed you at the beginning. And so in the absence of a new extreme thaw event, the active layer attachments and the retrogressive thaw slumps of the 2000 decade continued to grow back with vegetation, even as the mean annual temperatures increased. So as I mentioned, that anecdotally we had not seen much activity in this area in terms of retrogressive thaw slumps and active layer attachments, but there is an exception to that, as we have started to see quite a few of these things, or a few anyway, of these landslides, which you see in this picture here, which was taken by Ken Hill, who's actually on the call today, and this is a destabilized frozen debris lobe. And many of you are familiar with these things. They are frozen masses that typically move downhill slowly and remain vegetated. And I have an example here of a frozen debris lobe in Gates of the Arctic National Park. Here you can see in the top one, 1981, labeled 1. You can see this kind of lobe-shaped object here, largely vegetated and probably moving very slowly, just at most a few meters a year, creeping down slope. That's what they do when they are let's say, haven't been destabilized. And these have been studied intensively by our UAF colleagues, Darrow and Donnan and others. And and this one you can see in 2008. It had started to lose it a little bit here. You can see that there's some bare soil exposed and some stuff flowing off the front of this one. And then this destabilization progressed further in 2011. You can see this debris lobe has lost vegetation over larger areas, some areas of vegetation rafting down, big cracks forming. And then by 2019, it had become mostly destabilized, mostly unvegetated, and it actually flowed about 300 meters downhill. And the rate during that 2010 decade was about 30 meters a year at its most. And our colleagues here at UAF have studied these things in detail and have determined that it is deep thaw that destabilizes these frozen debris lobes and occasionally leads to real rapid movement up to 30 meters per year. So that's what's happened here in Gates of the Arctic Park. So after I saw these things going on, I went back and basically mapped the amount of bare ground that is occurring on frozen debris lobes to see if that had changed, and of course it had, and they were only occurred in study area 4. So here we are back to one of these bar graphs, and the amount of bare ground exposed on frozen debris lobes was smaller and more constant in episode 1, the 1980 AHAPS photos, and then still pretty modest in the 2000 decade Iconos, but then lately on the spot images in 2019, there was a lot more area exposed from destabilized frozen debris lobes. And so, what's going on that causes them to destabilize when the active layer attachments, et cetera, didn't? And so, what we think is going on is that these frozen debris lobes actually occur in the warmest part of my study area. This is the Arctic network, of course, where the mean annual top of permafrost temperatures prior to warming were not too cold, -1 to -2. And so these, of course, were the areas that I had highlighted in red and yellow previously that were most susceptible to permafrost destabilization in the sense of a deep talc formation and actual, not just an active layer thickening, but actual degradation of the permafrost and a formation of a talc and a persistent talc above the permafrost. And so that's what we think has happened to destabilize these frozen debris lobes, and they are symptoms of warming related deep thaw and talc formation in the warmest parts of Arctic network. At the same time that the colder areas, the active layer attachments and the retrogressive thaw slumps have generally been less active, thanks to, in general, stable permafrost and the absence of any new deep active layer thaw events. So that's most of what I have here today, and I think I've kind of run over time, but I'm sure we'd be interested in a discussion if you're interested too.
Yeah, excellent. Thank you, Dave. Right on time, actually. And you covered a lot of ground there.
Okay.
Really cool. Let's see. So we have 20 minutes here. We can maybe divide that in half and do 10 minutes of questions for Dave, and then go around the Zoom room and do a 10-minute member IRPIC member update if we want to. So with that, I'll open it up for any questions for Dave.
I have a question right off the bat.
Yeah, go ahead, Linda.
So my question is about, you're talking about, I mean, words, everyone pronounces them differently, talc, persistent talcs forming, but you're talking about in terrestrial permafrost, not under a water body. Is that correct? Because my understanding is that most talcs form underwater. I haven't heard about them forming in terrestrial permafrost. Could you describe that a little bit?
Sure. So, right, in what we'll put in air quotes here, normal situation, we would expect the permafrost to freeze back every winter, and the only big talcs or talcs, as you say, it can be either way, are underwater bodies. But if we have under warming conditions, then it's possible for the permafrost to thaw deeply enough that it actually doesn't manage to freeze back in the winter anywhere, right? And in fact, that's probably what happened in this frozen debris lobe that we're looking at here on the lower right-hand corner of the picture in this slide, is that because of the loss of the vegetation cover, this area has pretty deep snow, et cetera. It probably is now thawing back. It probably has thawed down, potentially 5 or even 10 meters, and that isn't freezing back now in the summer, and so that's also a talc layer. Then is that one that occurs between the zone of annual freeze back and the actual top of the permafrost, which is receding downward, and that is kind of what I'm most concerned about in the long term. Active layer thickening, of course, can have all kinds of important consequences, thermokarst, et cetera. But I think the really big landscape change that we might be facing here is if we start to see the permafrost receding downward and failing to freeze back in the winter, and we're actually developing then a talc over large areas of the landscape instead of being just under the water bodies where it belongs.
Nice. Yeah, thanks for the question, Lorene, and response, Dave.
To follow up on that, are there any studies or papers that have been done on that concept of a terrestrial talic?
Well,
Yeah.
gosh,
There's
I'm not sure.
there's
Ben
one
would
from
know better than me, probably. Yeah.
yeah, there's one from a group in Canada that I can share with you, Lorraine, that came out last year. It dealt more with permafrost peat plateaus and these kind of fen and thermokarst bog systems.
Mm-hmm.
And then I think as part of Vladimir's network at the GI, I think they've also detected this at a lot of their stations in the central and Arctic part of the network.
Okay, thank you. Appreciate it, Ben.
Mm-hmm. Dave, I'll follow up with a question real quick. If
Sure.
Do you have any sense about how this winter warming might be sorry about the background noise. About how this winter warming might be affecting the the cold weather inversions in the wintertime in these valleys as a potential driver of permafrost degradation?
Yeah. I don't know if Ken might be able to address that better than me. I mean, the assumption is that they aren't as strong as they used to be, right? And that's one of the main thing that's driving this warming. Although I don't have, you know, I don't have specific data on lapse rates or anything to back that up with.
Yeah, this is Ken. That's something we're kind of starting to look at, and so far, in the little analysis we've done, there hasn't been a big difference in warming at the sites we have that are high elevations versus lower elevations, but that is a question we're kind of looking at.
Yeah, cool, thanks. Yeah, thanks, Ken.
Hey, this is JJ. I got a question for Dave. Yeah, great talk. Enjoyed it. Great way to start the day. So my question is, just looking at these active layer detachment slides, my general conception of these things is, of course, that you get a wet summer, and as you're getting near peak active layer thickness towards the end of summer, you get some more rain and they let go. But just seeing some of the patterns in your analysis and some of the, I guess, the regional variability and timing, I'm a little curious. I mean, precipitation is a tough variable to really measure at a point, let alone over a big area. But thinking back to 2004, I remember that one as a very smoky summer. But I guess what my question is getting at is, has anybody ever looked at relationship between initiation of these features and, say, convective activity? So I'm curious if you get a situation like we had in 2004 where things stayed really warm, and I recall having a lot of thunderstorm activity pretty late in summer. And if you get that with a lot of rainfall locally, that maybe could explain some of the patchiness of this phenomenon. So you have any thoughts on kind of what type of precipitation event do you really need? Is it just a lot of rain no matter what? Or yeah, do you have any ideas there?
Yeah, that's I think that's a question that everybody's had trouble with, right? Because these detachment slides occur kind of suddenly in these remote places, and a lot of times we don't have good data on what exactly triggered it. So I think you look at the literature on these things, and there seems to be a relationship between both warmth and big precipitation events, and of course fires too. I mean, they definitely occur after fires. That's another one of these. In one study area here, some of these slides actually occurred in a tundra fire area, and that's something that's real common in the taiga. But I don't think any of us really have a good feel for, how much rain does it take, and when does that rain occur and stuff. I think I'm not aware of it. Maybe somebody else here does, but I'm not aware of anybody who has really been at the right place at the right time to catch that happening and really be able to quantify what it took to set these things off. We all just kind of have this general, kind of uneasy feeling that it's some combination of warmth and rain that does it.
We don't spend enough time in the field.
Yeah, well, we don't have enough cameras out, I guess, or something. I think, well, in weather stations too.
Hi, it's Peter Griffith.
Hi.
I don't know if you're familiar with a Yukon-based, I guess he's at Simon Fraser University, Brent Ward. He's been finding and mapping some fresh retrogressive thaw slumps in Yukon. This past August, I guess, got lucky to be like right on top of one within probably just a few days after it happened. So it might be interesting to chat with him about some of the things that he's found.
Right, thanks. And with any luck, they had some meteorological data then too, right?
Yeah, I'm not sure if he had that. We were able to task Digital Globe and try to get him a DEM, a difference DEM.
Okay.
And they're still working out to see if that's any good for them.
Mm-hmm.
The other thing I was thinking about is that in some of your areas, particularly in that northern, in the Arctic region, we've got, roughly a decade worth of airborne interferometric radar, and some of which includes estimates of soil moisture. It might be interesting for you to talk to Mata Mogadan about that, because it's possible that her P-band UAV SAR cuts across some of your sites, and I would think that these things would show up in an interferogram like crazy, and she might even be able to say something about soil moisture.
Mm-hmm. Yeah, and so what's the years that data is available for then, do you think?
She had a set of flights that I'm trying to remember if she started as long ago as 2010. Okay. With something called her Air Moss project, and then which was an Earth Venture suborbital field campaign. And then in 2017, we started flying those legacy lines of hers in that region. So we have 2017, 18, and 19. And hopefully, if not 2021, then 2022 we'll be back on that. One of the lines, we established a line in 2017, actually right along the Noatak River, but that would only cover the 2017 and on timeline.
Okay.
Yeah, great. Thank you. Thanks, Peter.
Yeah.
This is Ryan.
Yeah, go ahead.
Can I ask? Thanks. Hey, Dave, great presentation. And this may be a question for you or maybe for Ken. Have you guys looked into doing kind of a similar type work for the Central Park Network at all? Or is there any plans for that? Or?
Yeah, well, I think that Ken is hoping to get a detail to do some of this work in the Central Network. Although I think it's a little more challenging there in terms of mapping these features. One thing that to some degree made it easy in the Arctic Network was that we had a lot of these gentle vegetated slopes. That was where these features were occurring, and it made it really easy to map them. It's probably a little more challenging in Denali National Park and Wrangell's, where there are a lot of sort of less heavily vegetated landscapes, and that are sliding, and let's say not such textbook examples of the features too. Like what I was finding, in the Arctic Network were just really textbook examples of retrogressive thaw slumps and active layer attachments. And I spent a little time in Denali National Park, and there we seem to have lots of the kind of hybrid slope instability features of various kinds that are related to permafrost thaw, but are going to be a lot harder to try to, let's just say, understand, because there's more going on. You know, like the one at Pretty Rocks, the one that they've had so much trouble with severing the road, is neither of these, right? It's something else similar. And it's going to be hard to map them, although that certainly is something that we should be thinking about doing. I don't know that we don't have, I don't think we have specific plans to attempt that at the moment, because but I think it certainly would be interesting to do, but more challenging.
And if I could ask one more follow-up, is there any kind of water chemistry work being done, like within any of these watersheds at all, to look at how some of these might be impacting that?
Well, we have sort of general water quality monitoring going on in the parks. It's not targeted towards places that have these in them, though. It's sort of you know, we have a sample design of you know, for example, we've got a small lakes monitoring program that involves one of these grit sample designs, where they are looking at water quality at a bunch of different places, and we also are doing some water quality in the larger lakes and in the rivers. And it's not targeted, though, to where any of these features occur. So I think it would be kind of hit or miss whether or not we picked up the signal from these slumps. One thing that impressed me about them is that, you know, as many as I found, they are a fairly small feature on the landscape in terms of area. And so unless you happen to catch one of the little lakes that's right at the foot of one of these things, you're probably not going to see a signal from it. Although locally, they can completely silt up a lake, right? I mean, you can even see them on the satellite image. You're looking around and all the lakes are nice dark colored, and then there'll be one that's almost white on the satellite image, and then there's a slump next to it. It's like, okay, that's what's going on. And I don't know if we'll be lucky enough that our sample design for the water quality is going to pick any of these up. We aren't targeting them specifically that I'm aware of.
Great, thank you.
Yeah, thanks. Great questions, Ryan. It actually kind of triggered a burning question for me now, so I got to self-moderate, but I think it'll be a pretty quick question, Dave. Could you go back to that slide of Wrangell St. Elias that you showed the model ground temperatures of?
Sure.
I was just curious if you consider that area of the kind of the debris-laden part of the stagnant ice there in the Malaspina Glacier, where it says no permafrost. Do you consider that to be permafrost there?
So
on the Malaspina Piedmont lobe there?
Yeah, you know what I think?
mean, it's all like stagnant glacier ice there.
Yeah, we're talking about where I've got my arrow right now. Is that what you're looking at, or we're looking at? Let's see. Well, anyway, I know what you're talking about. Is some of these stagnant ice. So you know, the permafrost model took it's modeling the temperature at the top of the permafrost, and based on climatic features and surface characteristics, soil, etc. So I think that on the stagnant ice, I think in most of these places with the stagnant ice, yeah, okay, I see what you mean. Now we're talking about the Malaspina Glacier. I was thinking of the ones in the interior, but the Malaspina Glacier is definitely.
Yeah, the Malaspina lobe there.
Yeah,
that's
right. Yeah. Okay. So I think what the model does with that is it's modeling the mean annual ground temperature at the top of the permafrost, and if there is one of these persistent tailix. So in other words, yeah, I mean, a buried glacier is permafrost because it's material that's sub-freezing year-round, right? So that's permafrost. But in terms of this model, what he's tried to do is map areas that, if an area is one of these places that has a persistent talic year-round, then that will get mapped as non-permafrost. Okay, I mean, you know, and actually Santosh on his maps, I think in his legend he writes instead of no permafrost, he writes talic. or no permafrost, right? Because it's in some places it's where there was no permafrost and still isn't, but in other places that the model finds what's now above freezing temperatures at the top of the permafrost, which means a talus is forming, and it's going to take forever to actually get rid of all that permafrost down deep, but the map shows it as being above zero. So does that make sense? I was a little bit garbled.
Yeah, that makes sense. Yeah, I was just kind of trying to segue into like maybe a feature that you guys could potentially consider as monitoring, just due to how dynamic that area is and how much thermokarst is going on there.
Yeah, it's a super interesting area for glacial thermokarst in action, isn't it? And
yeah, it's fantastic there. Yeah,
and I should say that what Panda et al. Did with this GIPL model was to project into the future and locate places where these persistent talus should form, and based on their predictions, in other words, where the temperatures in the ground would go above freezing, and then those are labeled on their maps, and the idea then was that these are places where the temperature has gone above freezing at the bottom of the seasonally freezing layer, and that talus is progressively moving down into the ground, but as people who've monitored that phenomenon, for example, on fires where a persistent talus has developed and is continuing to grow, it can take decades, centuries, thousands of years to get through a thick layer of permafrost. So the permafrost is going to persist for a long time, beyond when we have written that it's above zero based on our model.
Yeah, cool. Yeah, thanks, Dave. And sorry everybody for being a bad moderator and not opening it up for this general discussion at the end, but it was a really cool presentation and nice question and answer session there, Dave. So thanks.
Yeah, thanks.
I believe Meredith has to hop off here to facilitate another Zoom meeting at 10 a.m. So with that, I'll say thank you. See you guys at the next terrestrial team meeting with NASA above, and then at the next Permafrost Collaboration Team meeting, whatever that might be next